Landon, how are you?
Really tired.
Tired?
Morning, Doug.
Let's have a nap day. How's that music working for you?
I can only faintly hear it.
Good stuff, huh? It's a good thing to study engineering by, I would say. Let's see. All right, let's share screen and get this going. All right, so what we are going to look at today, and we're slowing down quite a little through chapter 15. We're actually just doing 15.3 today, and we'll do 15.4 impacts and so forth next week. So what are we looking at today? We are looking at this business here, conservation. We've been talking about momentum and impulse. And now we're going to look at something kind of cool. There's only a couple of questions in your assignment. Since we're studying 15.3 today, there's only a couple of them. One of them is challenging, and I'll warn you about that in a little bit, but you're only doing 43 and 55 out of 15.3. So I got a couple problems dialed up to help us make sense of those. So let's stare at these for just a little bit. So collisions when objects stick together, and we're gonna start off with this exact example, but just as a for instance, let's say this car is moving along. This car is moving along at whatever, 3 meters a second. That's not right. And some other, let's say a motorcycle, put 2 wheels on this motorcycle, bam, smacks into the back of this thing and gets stuck to it. Notice I said objects stick together. That's kind of an awkward thing in this case. The example we'll do in a minute is a bullet going into a piece of wood. That's a little more natural for that to stick together. But you can appreciate the car naturally would have a lot more momentum to it just because it's so much more massive, so much heavier and so forth. And so the motorcycle is not going to really affect it as much because it doesn't weigh as much. It has less momentum. But remember, momentum is not just weight, it's also speed. And so the motorcycle could be really flying. But basically the idea behind conservation of momentum is if you kind of have the motor, let's put the car here. If you have the car here that has its momentum, its mass and its velocity combined, and then you smack into it with the motorcycle. And notice both of these are going to the right. So in our case, they'd both be positive. But remember, they could be going the other way. This could be a head-on collision where the car is over here going this way and the motorcycle is coming this direction and they smack into each other. And you might appreciate that if they're going the same speed, the car is going to win that race. And so in the end, the car would continue to go this direction, but it would be going slower now that it has the motorcycle on board. So the fact that this, one of the things really important in this section is, what direction is all this stuff going? And mass won't have a sign to it. It'll always be positive, but velocity, if it's going right, it will be positive. And if it's going left, it'll be negative. And so in that case, they would work against each other. And the result is the system, when plugged together, where both of the masses are added together, will have a new velocity. And so that's kind of what we want to play around with a little bit here. And so, I don't know, just to make a little bit more sense of this, let's stare at an example kind of like that, just to kind of kick this off. Let's see, let's get a new piece of paper. 15.3. Let's kind of look at an intro. So let's say we do have I won't struggle with my art this time. I will just say we have this car. Let's see, let's give it a mass, but remember mass is awesome if you're in metric, but let's give it pounds. So let's say this is a 3,000 pound car traveling this way, and let's even make it challenging, like at say 45 miles per hour. And over here, as I said, let's have something smaller. Actually, let's just make it another car. Except for we'll say this is a Geo Metro that only weighs 1,200 pounds, a tiny car. We're going to give them a head-on collision. Won't that be fun? And we'll say this car is going 70 miles per hour. So the question is, does it make sense? You don't really have necessarily quite as sure of an idea who's going to win. Like you got to think a little bit here because one is light but fast. The other was slow but heavy. So they're going to smack into each other. And so we're kind of wondering what's going to happen. And so it's not hard to multiply those to find their momentum and see which one's bigger to tell which is going to win, but you at least got to do that, right? It doesn't look much like a 70. So the idea behind this formula that we were looking at, the conservation of momentum, since these are going to stick together. So now we're going to say cars, big jumble of junk. And of course, we're ignoring friction and all of that. We're just trying to get the basic idea here. If they're skidding and rubber on road and stuff, this is more complicated in terms of friction, which makes it a little more interesting. But so if I call this car one and car two, then of course we'd say mass of car one times the velocity of car one plus the mass of car two times the velocity of car two would have to equal their combined masses and their brand new velocity. 1/2. Let's see. So do the units matter? Like the fact that I gave the speed in miles per hour, does it have to be feet per second? Notice the weight is in pounds, and that's kind of the standard unit. But do I need to convert this to feet per second, which is sort of the standard, or does it not matter? What's your thoughts based on the formula? What's your thoughts? You're up, Evold. What's your guess?
Maybe it doesn't really matter.
Yeah, you're right. In this case, because in the end, we'd kind of like to know the velocity in miles per hour because that's the only way we think about it, right? Because of driving. And so as long as all the velocities are in the same unit, I guess it wouldn't really make any difference. If you just look at that algebraically, if you just look at that equation as an algebraic statement. So I don't know, I guess we'll just leave it alone. See what happens. All I really want to do is acquaint you with this formula a little bit if you haven't seen it before. So if I throw in all my numbers, what am I doing wrong here? Lots of things are wrong there. What's wrong?
Mass is not 3,000 pounds.
That's a force, not a mass. So I've got to convert that to mass since force is mass. We've seen this before, but since force is mass times acceleration, then of course, if I just want mass, then I'm going to have to divide both sides by acceleration. So I got to take a force and divide by acceleration to get mass in our system. So, okay, I fixed that. What else is wrong? Alluded to this earlier. Very important.
Let's see. The 70 must be negative.
Exactly. So
Yeah.
velocity direction makes a difference. Velocity is directional. One's going left, one's going right.
Mm.
So these are not going to work together. And I alluded to this yesterday, but again, this is like a kid pushing, a parent pushing a kid on a swing set. If the kid is swinging toward the parent and they push them right then, that's a collision and it's not going to be enjoyable. That's what we got. We got one pushing, we got the kid swinging this way, we got the parent pushing this way. One's positive, one's negative, not good. Usually what happens is the kid makes it to the top and starts to go this way, and then the parent comes along, and so they're both positive and you're actually helping. And so this isn't helping. These are competing against each other. And of course, we know the masses combined. So together that's 4,200 pounds, but again, I'd have to divide by 32.2. Notice, interestingly, everything is divided by 32.2. So actually, had we not done that, we would have got away with it. Do you see that? Had we not divided by 32.2, it's actually both sides have it. So that's kind of interesting to note. So there's only one unknown. So we're going to see what that velocity is. If it comes out positive, that means the car won. If it comes out negative, that means car 2 won. But not only can we kind of figure out who won, we can actually figure out how fast this sort of ball of this chunk of metal is actually going to be traveling. So anyway, I'll leave the numbers alone, type it all in real quick. Plug and chug, as we say. 1200 divided by 32.2 times negative 70. Boom, on this side I got a positive 1583.85. 4200 divided by 32.2 gives me 130.43 times velocity of kind of 1 and 2 combined. So I'm going to get a positive number. If I didn't type something in wrong, double checking really quick. I don't see anything. Divided by 130. I got 12 positive. V of the combined mass positive 12.14 miles per hour. We'll just call it 12.1. So that kind of feels right, doesn't it? Feels like, yeah, the small car is going to lose in this case. But again, the only reason it lost is because it wasn't going fast enough. We could take the second level and figure out how fast would that smaller car have to be going so that their momentums would be equal. Of course, that would just be when is 3,000 times 45 the same as 1,200 times some other number, and we could figure that out. And then and that's a good visual for inertia, what inertia is. So the little car isn't just a bullet, it's still got some mass. 1,200 pounds is a pretty good weight. It's not like it's nothing. You're still going to get smashed if it runs over you. But again, the concept that they have to stick together for this to happen is kind of an important one. If they bounce off of each other, you may have noticed in my note sheet, and again, I made this note sheet myself, so I added things that would speak. So when there are no impulsive forces, what does that mean? Well, none of these. No force times time. No other impulses are added. If they don't stick together, then it's really just the sum of the initial momentums will be the sum of the final momentums. What would that look like? What does it mean if two things don't stick together? Like, what would that look like? Can you think of an example of like, what would that be like?
Oh, then bouncing off?
Yeah. Yeah. Well, frankly, the cars are probably a good example of that, right? Except for in the case of the cars, they're not going to stick. They're going to stick together more because the car on the left was going 45. It hits this other car. Now it's only going 12. And so it's pushing the little Geo or whatever in front of it. But maybe a better example of something kind of bouncing off would be something like this. You've got again, just to make a boring physics example, but it's like if a block is kind of sliding along in this direction and then you throw a marble at it from behind, the marble hits the block. Does it make sense? The block is going to kind of go faster as a result of that, no matter what, but the marble could actually bounce off and go the other direction, right?
Yeah.
So, I mean, that's what this is saying. So then you say, okay, well, the initial momentum, some of them, the initial momentum of the block plus the initial momentum of the marble. They smack into each other and kind of sort of transfer energy, if you will, to each other. And now the velocity of the block is different, and the marble, which was positively velocityed, is now bouncing off to the left. We're assuming the block is kind of heavy and the marble's kind of small. Then it bounces off to the left, and now maybe it has a negative velocity, something like that. Maybe that's how that would behave. Does that concept make sense?
It's interesting that the coefficient restitution is showing up again immediately, because that was a big point of interest with the baseball analysis paper
That's
in
exactly
terms
right.
of how much energy was being lost.
That's exactly right. And that's what we're going to pick up. That note that's on there is actually for tomorrow's, because we are going to decide if anything is lost. So the example I was just talking about was, you know, the marble bounces into it and kind of nothing is lost. But since you brought it up and since it's right in front of us, the percent of energy remaining to rebound from a collision. So you don't get all your energy back. And typically there's going to be something lost in friction and in heat, you know, from a ball bouncing off a wall or something. And so we'll play around with that a little bit. And again, doesn't that feel like I guess I haven't thought of one ahead of time, but I'm thinking that also sounds like a good project. In other words, if I bounced, is there some way I could measure that myself? I mean, I don't like book problems, or they just tell me the coefficient of restitution is 80% or something like that. I'd rather like go bounce a ball. And is there some way I can measure this myself? Is there some way I can, like we did with the block sliding down the ramp for the project? You weren't there for that, Landon, but we measured the time it took to slide down the ramp, and based on the fact that it didn't get there when it would have had there been no friction, we were able to figure out how much friction there was. And that's kind of cool just to come up with those numbers yourself a little bit. But just to kind of play around with that second formula a little bit. Sum of the initial momentums will be equal to the sum of the final momentums. Notice the velocities, or the masses, aren't really changing, although that's not impossible. There could be some lost, but let's just play around with that a little bit and see if we can't make up an example and just kind of get a little smarter. So let's see, let's do the example that let's do this in metric, since we just did one in. So we'll say this block is sliding along. Let's keep it easy at, I don't know, 5 meters a second. It's cruising along, having a nice life, cruising along on this table. And we'll say it weighs, let's see, kilograms. So we don't have to fool with that. Let's say it weighs 3 kilograms. So all the units are kind of fine. And then we take this marble over here that's kind of lightweight, and we're going to send it after. So it has to be going faster to hit, but let's send it along at, I don't know, 7 meters a second. But let's give it 1.2 kilograms. So, you know, bang, they're going to smack into each other. And so the concept here, you know, what that formula is really titled is, and I think I said this in my note sheet, but this is really illustrating what's called the conservation. Just like the conservation of energy, this is the conservation of momentum. Just kind of gets transferred, just like energy did. It got transferred to something else. And so the same thing is here. So, okay, that seems to make pretty good sense. But notice this time they're both positive. And so if I say, all right, what's my sum of my initial momentums? Well, that seems pretty easy. Let's see, is this a good problem? I'm starting to doubt this problem all of a sudden. 1.2 kilograms times 7 meters per second. That's the in marbles. And then 3 kilograms times 5 meters per second. And then let's see, they bounce off. Well, that's not so good, because then we say, okay, well, I've got the mass of the marble times its velocity plus the mass of the block. We're assuming those haven't changed, but their velocities have changed, right? Velocity of the block. So that's not good. Don't I have two unknowns there? How am I supposed to know? How am I supposed to know how they're gonna behave? Seems like we should be able to figure this out, doesn't it?
Is the V block, is it the same as like a final velocity?
Yeah, in a sense.
Can we use the previous formula to find it?
Um,
Or is it not pretty much the same number?
so
Like that V1/2, is that not the same as VB?
well, the question is whether they stick together. Like in this case, the important part of this formula is they're now connected, whereas we're in our situation, we're kind of thinking they're bouncing off of each other. Does that make sense?
Yeah.
So there's not those aren't stuck together anymore. They're not going to have the same, they're not going to have the same exact velocities. Sort of feels like the marble's about to get a negative velocity because it's kind of lightweight. And the block should be moving a little faster. I mean, my gut instinct here is that, you know, like velocity of M should be something like, I don't know, -1 meter per second or something like that. And the velocity of the block should be going faster, like maybe 6 meters a second or something like that. Seems like that should happen. But of course, that equation's got two unknowns in it. So I'd have to have some.
Would I was going to say, would changing the frame of reference help at all? But I don't really think it would.
Yeah, frame of reference is an issue. And I just made this problem up just to, you know, give us something to think about, kind of what
Yeah.
conservation of momentum looks like. But I'm having the same reaction you are right now, which is, although this problem seems pretty simple, I find myself staring at it going, you know, it's not necessarily as obvious as you think, is it?
I was initially thinking that maybe we could simplify the problem by looking at it from a frame of reference is already moving in 5 meters per second to the right. So then we're basically looking at a block that's standing still and just a marble that's approaching it at 2 meters per second. But I'm not really sure that actually makes it any easier now that I'm thinking about it.
Yeah, that's an excellent idea because you're right. Frame of reference, you know, we think of things as not moving, but remember you're on a planet that's flying 66,000 miles an hour through the solar system right now. So you think you're not moving, but you're not moving relative to the Earth, but you're moving pretty darn fast relative to the sun and everything else out there, which is a little hard to get your mind around. Let's come back to that. I've got two problems to look at today, and the second one I think speaks to this a little bit. In other words, is there some other equation, sort of a second equation? I'm going to erase this since these aren't right. Is there some kind of second equation we could write for this that would also have the velocity of the marble and the velocity of the ball? And I'm actually, I just want to look at one thing. I may be asking a question here that actually kind of belongs in the impact problem. Like it might need this coefficient of restitution formula. Like that might be where our other one comes from. So I might be sort of stealing my thunder from tomorrow.
I'm not sure if just what's on the formula sheet actually helps that much. So, well, I guess. No, never mind. Actually, because if they're completely bouncing off, then we can say that it's 0.
Yeah. Well, the other way,
So then
100.
Yeah.
In other words, we get it all back if we put in.
Yeah, sorry, 100.
100% for E, which basically means nothing is lost, which feels pretty accurate. You know, if it's a a marble, which doesn't deform, like you were pointing out, Landon, that softball just totally deformed. E is not going to be 100% if that's the case. And so, I find myself wanting to play around with this, like, is a super ball going to be really good, even though it deforms, because it's actually springing back. Whereas, two things like a marble and a block, do they kind of thud into each other? And actually, it's not one, it's terrible. It's like 20%, like you lose a lot of it. And so yeah, I think it might involve tomorrow's formula. But anyway, let's go look at a couple examples that don't involve this. And if we have time, we'll go back and start talking about this today. And then if not, we'll tackle it when we get to next time. So the main thing for today, which I didn't really write down here, is just that we want the sum of for sort of the stick together. Really today, the whole stick together concept is really important. You have two masses that are going to either separate or they're going to come together. And that's the two problems we're going to look at today. The first problem, they're actually going to come together. This is a wonderful question. This is in your book, but it's a terrific one. So let's look at it. So I think this is old school in the sense that I think this literally is an invention designed to figure out how fast to estimate the speed of the bullet. So I don't know if you've ever shot guns much. I'm not a gun nut, but I have a couple guns. And when you buy bullets, it actually tells you on there based on the size of the bullet and how much grains is a weight measurement for gunpowder, and how much of that you have in there. It'll tell you what your muzzle speed is, and it'll be like, oh, this is a 1400 feet per second, bullet. That's how fast it's going to travel when it leaves your gun. That's what it says on the package, but it seems like, well, depending on the gun and maybe there's some variability. Well, this is pretty cool. So you got this ballistic pendulum. So it's this piece of wood. That's kind of cool to shoot into it because the bullet's going to embed itself. And it's a 4 kilogram wood block. And so good deal. It's metric, so I don't have to fart around with that. That's not a good color. I don't have to think about changing it as we did in my introductory example. So this is a 4 kilogram block of wood. It's at rest. And so its initial velocity is 0. So that's going to make our calculations a little easier. It's not moving. To Landon's point, which is kind of cool. Frame of reference, if this person was shooting that block, but that whole system was like on the bed of a train, what was ripping down the road at 50 miles an hour, it would still be not moving as far as the frame of reference of the train. And so it's kind of cool that you can think like that. So anyway, that has no momentum. So it's just sitting there resting. But of course, the bullet, which is 2 grams, grams, ding, 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 2 grams. I got to make that kilograms. So I got to think about that. So this thing is 2 grams, which when I divide by 1,000 is 2 thousandths of a kilogram. And so it's really lightweight. All right, 2, 1, 2, 3, 0, 0. Yeah, that's right. Suddenly doubted myself. So 2 thousandths of a kilogram, but of course it's moving along. Well, they actually don't tell us how fast it's moving. That's because the brilliance of this invention is we're going to use it to figure out how fast that bullet's moving. So that's kind of cool. So we sort of have a velocity of, I guess I'll say this is capital B for block and little b for bullet, unfortunately, are the same. So velocity of the bullet is, we don't really know. We don't know what it is. So let's think about our formula. So we have the kind of the sum of the momentum. So we got the mass of the block times the velocity of the block plus the mass of the bullet times the velocity of the bullet equals the 2 masses added together. Notice this is a case where they're quite naturally going to stick together. The velocity, I'll just say velocity, I guess. They're going to stick together in this case quite naturally because the bullet's going to embed itself in the block. So that's kind of cool. So that's going to be conserved. So this only works if they stick together. So we say, cool, well, we know lots of stuff here. Velocity of the block is nothing. So this whole thing goes away. We don't know this velocity, but we do know this is 0.002. And we do know this would be 4.002 now that they're stuck together, right? So it just got 2 grams got added to the 4 kilograms. And so it's actually going to weigh more. So we don't know either of those velocities. And so aren't we kind of stuck here too? And the answer is yeah, without something else, we're totally stuck. Now, in this case, they hung it from some ropes. They shot it and it flung just like they showed that image there. And then they took some more measurements. And so we are stuck, just like we were in the example I made up a second ago, in the sense that we got 2 unknowns, but they took a measurement of something. And so that's kind of cool. And it swung up in the air. It must be like time-lapse photography or something. I sure would love to try this out. I just don't know how, with kind of the ordinary items you have in your house, how you'd be able to pull this off. I think a slow-mo, just a regular camera on slow-mo, if we had the camera sitting there next to a tree or something, and it was just aiming at the block and we went back and shot it, do you think it would capture that? Would it be so quick? All we really would need is to be able to get an estimate for that angle right there. So they're telling us that it swung up so that that angle right there was 6 degrees. And they're also telling us how long the chords were on this thing. And so, what good does that do? So we can kind of see the energy of this bullet got transferred into the system. And so to me, this feels like, well, kind of like last week, like energy.
Yeah.
Don't we have work being done here? Like energy is being conserved. We have distances. I'm feeling like we have forces times distances here to consider. Are you seeing that too? What's your initial thoughts on that? Again, let's just go ahead.
My initial thought would be that if we can find just the change in height, all the energy that's turned into potential energy there, assuming that it's not moving when it hits that angle, should work if energy is being conserved. But the fact that the bullet is sticking to the block makes me think this is an inelastic collision potentially. So maybe we're losing some energy there. I'm not sure.
Yeah, well, it's because it's stuck in it. I don't think we're losing anything. The only question would be whether the block kind of hops. I think the block would have to be heavy enough that when you shot it, it didn't get all bouncy. It would have to just kind of go swing and so forth. But again, the best way to do anything in math is not to act somehow like you're just supposed to immediately know all the steps to take. Anytime I look at things and I'm not sure, I just start writing stuff down. And so I'm interested in kind of the conservation of energy equations now. And I'm just wondering if that's of any good. Like, so what if it's not? Who cares? I mean, this is kind of cool, but I see this, the block got lifted in the air, right? It got lifted a certain amount. And so let's think about those equations. I'm just rewriting them here, but I don't know about you, but it only takes like a week and I already stare at these things and go, wait a second, I got to get all this back again. And I've taught this numerous times, but let's see, 1/2 mv squared. Okay, yeah, that's right. That's kinetic energy. So that's kinetic energy, or sort of like energy that relates to speed. And then work. So those are the same exact units we looked at last time. Work is a force times the distance. So we had kind of an initial kinetic energy for this thing. And then work is done to it. And then we end up with a final kinetic energy. This is what I'm thinking. Something like that. Let's see, was that what our formula was? Let's take a look at our formula sheet. So I really got 2 choices here. I've kind of got the one that I just wrote down. but I've also got the conservation of energy, which really kind of allows you to add work at the end as well. So maybe I'll add that to it.
Well, if you really think about it, just using the initial one, the work that's being done is kind of being done before the final state, if that makes sense. So the final state is the block and bullet combined, not moving.
That's right. So would you agree the final velocity of this thing is 0? So that's not moving. And initially, it had a distance of 0. In other words, it was just sitting here. This is its initial position. So it's just sitting there. It hasn't been moved. But it did have an initial velocity, right? And in this case, kind of that that V0 is actually the same as our V there. In other words, that's the V we don't know from above, isn't it? So I know that, and again, we're thinking of this as just like the instant after, just after impact. So now the block actually is moving, because remember, it's going to slow down. It's going to start slowing down immediately. So for that reason, I have all of the mass combined. So I got some speed that it started out with. And that speed, kind of that kinetic energy, actually turned into work. I think this is going to go somewhere, don't you? Well, work is a force times the distance, and really the force involved here is straight up and down. In other words, that's just the weight of that thing. Force is a mass times acceleration. So that force is our mass of 4.002 times our acceleration of gravity, 9.81. So that's the force of the block. And then it got lifted a distance. And because this is straight down, then we're talking about a distance that's straight up. In other words, what I got to figure out is kind of like that distance right there. That's our distance. How much did it get lifted up in the air? And will trigonometry let us figure that out? So let's see if this is also 1.25, that length of that string and the length of that string. But this creates a right triangle. Let's see, I guess the right triangle would be here. Does that help? I can see angles and lengths, and I think right triangles. Does that help?
I want to say that doesn't quite work because the you won't actually be getting 1.25 on the vertical cable there.
I thought it's maybe from the corner to the corner distance, you know? Whereas because we're gonna have, we know two distances and an angle. So maybe we have to find the distance from the end of the rope before the bullet hit and to the distance, the final distance.
Yeah, so you're saying like over here, like.
Yeah, that one, yep.
So the answer to that is yes, except for if that's the case, then you got to figure out the force in that direction, and that's hard. That's why I'm saying if we let the force be straight down and then we have the distance be straight down, that's safer. Now take a little closer look at this picture over here though. For the right triangle, as Landon pointed out, that comes up a little short, right?
Yeah.
But that's actually a good thing. Why is that a good thing?
Oh, because the difference between the actual height and the 1.25 is the distance we're looking for.
That's exactly right. So if I say, I'll just say h for height, I could say the cosine of 6 degrees is adjacent over hypotenuse. And if I do 1 point, make sure I'm in degree mode, 1.25 times the cosine of 6, I get 1.243. Then that means D, if I take 1.25 away from that, wow, that's a really small number. Feels like it needs to be really, something feels wrong with that for some reason. So that means D is, I left all these numbers in my calculator. I'm going to call it 0.0068. So basically, this energy over here got turned into, if I switch out that D now for 0.0068, that basically lifted that block straight up in the air. We actually don't care what direction it went. Kind of, you know, it actually curved. Do you realize how hard that would be? To your point, Evel, in order for it to kind of slide over here, it didn't even go straight. It actually kind of curved its way up to that location. So it's so much easier if I think of it as just a force and a distance, and the force and the distance have to go in the same direction, just like they did in statics when we took force times distance and called that the moment. It's got to go in the same direction. So my force is straight down, my distance is straight up. Hey, that's kind of cool. That means I've only got 2.001. That's a half of 4.002 times that initial velocity squared. That equals whatever that all is multiplied out. I think I'll just write it out for now.
Yeah, drawing's almost a little bit deceptive because you kind of forget how small 6 degrees is looking at the drawing.
Good point, because yeah, they drew that more like 20 degrees. So you're right. That's why I felt like it was wrong. A distance of 0.0068. Ooh, that's hard to measure. Interestingly, I wonder, you know, I wonder if they had some way of measuring that. I wonder if there was some almost like, here's the rope coming down, and they had some kind of a something hanging against it. So when the rope went this way, this thing would move up, and then when the rope went back, it would stay there. So then they could walk over there and just measure that angle. I wonder if that was actually, I wonder if that's a thing.
It'd definitely be a smart way to do it, I think.
Seems like it, because like the time lapse photography thing, or you know, trying to somehow measure that distance, like even what I was thinking with like a ruler on the wall behind it if you took a picture or something. But that just seems rough.
I know with like what are they called? The one of the methods I've seen before, there's this guy who's testing the tensile strength of 3D printed parts using different techniques.
Interesting.
And the way he did it was just by putting, well, it's a different process, but he used a visual process where he just had a camera focused on it, and then put just 2 little dots of the Sharpie, and then monitored how it went, you know, how it deformed, and had like time sync to his like pressure sensor on the device.
Yeah, that's pretty brilliant. So if I don't screw this up, I get 0.1334 for the velocity squared, which means that initial velocity is 0.365 meters per second. But what is that velocity? Like, what is that of? Because I'm thinking that's not very fast for the bullet. That can't be true. What's going on here?
Oh, that's the velocity of the block and bullet.
Yeah, that was combined. This is the combined. So that's pretty cool. But how does that relate back to our problem? Because back here we were saying, hey, I'm stuck. I've got 2 velocities I don't know. Did we just figure one of those out?
The other thought is that I just had is instead of plugging it back into plugging that value back in and going from there, wouldn't it also be possible to just set up the original conservation of energy equation to instead use the mass of the bullet itself, then find the velocity that way?
Yeah, in other words, combine them. In other words, you're looking down here, seeing 4.002 in velocity, and like we also had that down here. And so could we kind of combine these a little bit? I think the answer to that is very.
I know, I was actually just thinking the original conservation of energy equation, because we know all the energy is coming from the bullet in the first place. Instead of having to worry about the speed of the block at all, we could kind of just sidestep that and just use the mass value for the bullet, right?
Yeah. In other words, you're looking back here and saying, you're kind of looking at that, saying all the energy for this came from that. And so now, and effectively, that's exactly what we're doing. Since this term over here was effectively 0, we're really coming back here and saying, we now know this number right here. Since that was the combined block and the bullet, then this is where the 0.365 meters per second goes.
Yeah, I mean, what I was thinking is that maybe you don't even need to know the velocity of the block at all, though, to solve the problem. Because if you just set up the just setting up the conservation of energy equation, instead of using the mass of the block, we just, in red down there, we just instead just use the mass of the bullet. Wouldn't that instead just produce find the speed of the bullet immediately without ever having to worry about the speed of the block?
Got it. So you're saying, well, let's check it and see. I see what you're saying now. You're basically saying if we went here, why don't we just do this with 0.002 instead of 4.002, right?
Yep.
Let's try that. I think you may be right. So certainly in this case now, at least in what I have sitting up here, I know I could say 0.002 times the velocity of the bullet equals 4.002 times the velocity of them combined. We now know that that's the case. And so I say, okay, cool. I got 0.365 in my calculator, multiplied by 4.002. Get that answer and then divide by 0.002. And then boom, I get my final answer, which feels like it should be in black. The velocity of the bullet itself is about 731 meters per second. Okay, so what you're saying, so you're saying, let's just try this out. You're saying if we took I'm just rewriting the red conservation of energy equation. Tell me if this is your idea. So I'm just rewriting it, except for all I have is the velocity of the block. Is that true? Does that produce the same answer? I don't know. I got 16.
Yeah. Huh. I feel like it should work, but I'm not sure why it doesn't.
Well, my thought is the work that's done over here was the work required to lift a heavy block. Does that make sense? Like it had to lift a heavy block, not just the bullet.
Yeah, my thought, I was kind of working at this from looking at the just conservation of energy equation, where we're thinking about, kinetic energy plus potential energy equals kinetic energy plus potential energy.
Yeah. I think you're right. I'm going off an intuition too.
Yeah, it sounds like it should be right.
I think we just have to fool around with it a little bit more.
Yeah.
But what I try to model in all my classes when I teach, just because I inevitably like what you just said, Landon, as an example, is, you know, you said something, you know, off the cuff that you were wondering about. And my first thought was, just as a fellow human being, like, I don't know. I'm not sure. I don't, you know, I don't immediately know the answer to that question. Well, that's what it sounds like to students. When I say something and I'm, you know, hopefully I'm right, I'm not just guessing, but I say, here's what you do. Well, when you first hear that, you think, I don't understand what you're saying. Like, I got to think about that. I got to play with that. I got to work with that a little bit. And everybody kind of has different things to work with and different amounts of time to spend and so forth. But that's why I think the most important thing is to just say, well, I got a few equations here that I can work with. And so let's just start writing them down. In the end, though, notice what I wrote here is a total mess. Like if I just sent this to somebody else and said, hey, look, here's how to solve this problem, that's gobbledygook, because I actually started at the top, had to hit pause, went down to the bottom, then I took the numbers from the bottom, put them back up in the top. Like that does not show logical train of thought at all. So, you know, if the goal here was to like teach the police academy how to do this, I failed miserably. Would you agree? Like what we need to do is what Landon said, which is, because they don't want to learn dynamics and physics. They just want to figure out how fast their bullet was going. Like we want to reduce this to, you know, what measurement do I need to take? In the end, what they'd really like to do is just plug in 6 degrees and have it spit out 731. Does that make sense? Like make a spreadsheet where you just put in the angle and then boom, out pops the answer. Maybe you put the angle in and the bullet size, because there are different bullet sizes, right? But the block of wood's always the same. Well, maybe not, because you're shooting a full bullet. So every shot it weighs more, right?
My other thought is that it makes sense that conservation of energy is conserved in terms of the movement of the block. In terms of like the block moving to a certain height, that makes total sense. But we're not necessarily assuming that conservation of energy is conserved in the whole system necessarily, because I want to say that if conservation of energy was being conserved, this would be a completely elastic impact. So that the bullet probably, for that to work, the bullet probably couldn't be stuck in the block for that to work out. That's what I want to say, you know, intuitively remembering physics from a couple of years ago.
Yeah.
But I think that's it.
You're right. As always, these problems are, you know, a little bit of an oversimplification. But, you know, one of the reasons I like this question is because, you know, there might be details to it. In other words, like if the bullet is not shot exactly straight, you know, how does it enter the wood? Does it matter how it enters the wood? Is there something lost there? Irrespective of all of this, it's actually given me a number that's probably reasonably close, and maybe that's all I care about. Maybe that's like, hey, that's in the ballpark.
Actually, I think the reason why it isn't working out is not a problem simplification issue. It's actually just that necessarily energy is not being conserved. Well, you know,
we're saying it is
in terms of like, well, the energy of the block getting moved up, that is being conserved. But for the actual just now, like even just looking at the basic math of this, because we know looking at the conservation of momentum equation, we can kind of just take that equation and plug both sides into, you know, 1/2 mv squared and see how it works out, because we have all the values now.
For your satisfaction in this, I would absolutely think.
Yeah, I'm gonna go ahead and write that down real quick, because I
think
I might be able to find out how much. I think I can find out how much energy is actually being lost here, unless I'm completely wrong.
Try it. I'm gonna take just a second here to maybe clean up this note sheet just a hair, but I want to see if we move that down to there. Evold, how you doing with this? Does this feel okay to you?
well, after from the notes you did, I got it. I mean, it's not really bad.
Yeah.
Um, it's just I wish we can spend like one more class on it, or make like a in-person project.
Yeah.
You can shoot things.
Yeah. I'm not opposed to that idea. It's nothing saying we can't go out shooting somewhere. It's not like it has to be a class sponsored project.
Oh, wow. Did I do my math right? Oh dear. I think I did my math wrong. Let me double check this. Oh no, I did my math right, I think. Oh dear.
Because we're definitely treating this as though everything is conserved, which in a sense it practically is pretty darn close. All right, I want to show you something else that's ridiculously humorous and cool all rolled into one.
I'll be right back. Hold on a second.
Okay. Take a look at this. Speaking of crazy things to do, let me see here. I'm going to share a screen because I seem to have linked a video for this, so I might as well.
I saw this video on the YouTube.
You did? How? How in the world did you see that?
Well, I don't know. YouTube is a really weird place.
Let's see. I gotta find it. I want to be able to link that. It was on a PDF file, so I can't get to that link very easily, but I know where it is. So all the sample problems I made for this class are Word documented, so I just have to pull that up and click on it, and we should be able to go there without having to type it in and find it. I probably could have Google searched it faster than this, but
I just want to say, you know how unsafe that is?
yeah, I have to kind of provide the disclaimer that I'm not suggesting you go try this. But I remember this video, and the guy, he must be decent with a gun and with a skateboard because it didn't work out. It worked out okay for him. It's not a very good link. Oh yeah, it is. He started hauling. He is pretty good on a skateboard and a gun because that could knock you over really easy. He put off a ton of shots there too. Oh my gosh. Yeah, terrible idea. I'm a little on the crazy side, but I wouldn't even try that one. Well, let's see if we can figure this out. So this question's unique. And by the way, these questions are, funnish or interesting, but these are very similar to the two questions I'm assigning. The difference with this one, though, is the fact that it's kind of the opposite. Like in the previous problem, you had a bullet and a block separated, and then the bullet got into the block, and then the block started moving. Whereas this is kind of the reverse. This is like the guy and the bullet are connected, and then he shoots the gun, and now they're not connected. Does that make sense? It's like they're coming apart. It's like the bullet flies out of the wood. Do you see the difference? So this is the setup. We got this under, and I'm saying 180 pounds. So that's everything: the man, the gun, the bullet, and the skateboard, everything put together. So we got his weight And of course, the bullet doesn't weigh much, but we're gonna have to know that because it's gonna separate. We don't need to know the skateboard and the gun. We don't need to know the rest of that stuff. But the bullet, which I'm seeing weighs 0.2 pounds and has a muzzle velocity according to the block of the according to the ammunition box. And by the way, those are fairly reasonable numbers.
Mhm.
So basically, as soon as he shoots it, he's going to be 179.8 pounds, I guess. Does that make sense? So
Mhm.
right now, 180, boom, shoot, then it takes off. And so this feels initially like, oh, this isn't going to be hard. This is kind of the same question, but it's kind of like in reverse. Does that make sense? It's like you have the mass of the mass of the dude plus the mass of the bullet times its velocity. And this is really kind of like before he shoots. And in our case, of course, he's going to fire one bullet and then we're just going to see what happens instead of like 40 like he just did. And then after he shoots, since this is conserved, after, should get a T in there so I'm retarded. After, then we got the mass of the dude times the velocity of the dude plus the mass of the bullet times the velocity of the bullet. Does that make sense?
That's pretty simple.
So D for dude,
516.
B for bullet. And I guess I don't really need to say velocity 3. I'll just say velocity. So I don't know. Is that enough? Like, what do we know?
Well, we know the entire left side of the equation is going to be 0 because we're not moving right now.
That's exactly right. So before, his velocity is actually nothing. So we know his whole mass, it's 180, which I guess I'll throw in here. Although it's not 180, right? Because this is pounds, so I actually have to divide, but it doesn't really matter because his velocity is 0. And I know the mass of the dude is 179.8.
Yeah, I'd argue we could probably ignore the mass conversion because it's going to get canceled out anyway.
Yeah, I think you're probably right. Just like in the last problem, we could ignore the 32.2 if we wanted to here to clean this up. Even if we wrote it down, we could start by saying, hey, look, everything's got that, and let's multiply both sides by 32.2. So you're right. But do you see how we're kind of in the same spot again? It's like, well, that's great, except for I don't know either the velocity of the dude or the bullet. Well, I do know the bullet's
Well, yeah.
2800.
Mhm.
But there's a complexity to this, and you have a problem in your assignment 55 where it's like a cannon that it's kind of cool because this cannon sort of rolls down the hill. So it actually has an initial velocity. Our guy didn't have a velocity at all, but this cannon rolls down a hill. So it actually picks up some velocity. And then when it gets to the bottom, so now it has an initial velocity, unlike ours, then the cannon fires a bullet out of the side of it. And this is remarkably complicated. So it's like, what do I do with this? Well, as I said, you might be tempted to just say, well, the velocity of the bullet is 2800.
But we also have to think about direction, right? Do you want the guy to be going forward or backward here?
Yeah, that's a good question. So we'll use the picture and say that's positive and that's negative. So the bullet's going to go right and the guy's going to go left. And so that's right. The bullet's velocity is going to be positive, but the dude's velocity is actually going to be negative. So you might be tempted to put 2800 in there, but will it be 2800? I want you to think about that. If the guy stands still and shoots, then the bullet goes 2,800.
Mhm.
But does it go 2,800 if he's moving away from it?
Yeah, it's easy enough to do for the first shot, but after that it gets a little more complicated, doesn't it?
Yeah, it's kind of the old, what if I was in a car traveling down the road and I shot a bullet, forward, then does the bullet go faster or not? Well, it gets back to what Landon said about frame of reference.
Yeah.
So the answer is it does go faster if you're a person standing beside the road. So with the earth as a frame of reference, the bullet will go faster if you shoot it out the front of the car. But if you're in the car, it's not relative to you. So that's the issue here. So here's the thinking. So here's the idea. If the gun is sitting here, we'll just draw a simple representation of a gun, and you fire the bullet out this direction, what does all of that look like? Well, the gun's going to go this, or the velocity of the bullet's going to be going this direction, but the gun itself is being allowed to move, which means it's actually going to head off in that direction. So for instance, if this was say 2,700 and this was negative 100, that would work as an example. And I'm not saying it is 100 and 2,700, but the 2,800 is relative to the guy. Does that make sense? It's not relative to the ground, it's relative to the guy. So if he's looking at the bullet, he's going to think, hey, look, that bullet's going 2,800, but he doesn't realize he's moving. Does that make sense? Kind of simultaneously, he starts moving.
That kind of simplifies things a lot, doesn't it? Because if you always make the frame of reference, regardless of your current position, being on the guy, then you could kind of just record the gain in velocity along the way for each step. And then the only variable you'd actually need to change for your calculation would be the number of shots fired, essentially.
That's correct. Like in his case, because he shot a whole bunch of them, right? That's right. So in the end, because of this picture that I just drew right here, really this is the formula. The velocity of the bullet will be equal to the velocity of the dude plus the velocity of the bullet with respect to the dude. In other words, that's the speed the dude sees. And so in our case, where does the 2,800 go? It does not go here. The velocity of the bullet is not 2,800. Well, that's if we let the ground be the frame of reference. Does that make sense? And that's in a sense the easiest way to think about this. For that reason, that is where the 2,800 goes. You see what I'm saying? So up here, we got to the place that we got, and we sort of got stuck, and we said, one equation and two unknowns. Well, don't like that. Is there some other equation I could write? Well, in this case, yeah, it's a frame of reference equation. I mean, there was information up here, like there was 2,800 and we never got it into our black equation, right? So it's like, where does that go? Where do I put it for D? Do I put it for B? The answer is sort of neither. I've got to come up with an equation that relates these two things. So if I say my second equation is the velocity of the bullet equals the velocity of the dude plus 2,800, that's where the 2,800 goes. Now I've got two equations, two unknowns. 2 equations and 2 unknowns. Cool. Now, are you okay with that equation? Are you happy with that? Is that true? So as an example, I mean, this isn't the right answer, but if I just go take the numbers that I used a second ago, the velocity of the dude, the gun, in other words, the gun and the dude are the same thing. That'd be negative 100 because it's going left. The velocity of the bullet then would have to be 2,700. That's where that equation came from. That's why I wrote that equation that way. It works like that. But the signs are, a problem. Like you got to be careful not to mix this up, if you will. And of course, in this case, the bullet goes one way and the guy goes the other. And that's kind of similar to what's going to happen in your kind of canon problem in your assignment. So that's why I wrote that equation that way, just to try to capture the fact that the speed of the bullet relative to the guy would be 2,800. But an observer is going to see 2,700 for the bullet speed. Basically, that's the idea here.
So I've got this is maybe more of a notation question than an actual math question, but assuming we started not moving and we wanted to find how fast we were going after, let's say, n number of bullets are fired, would the best notation for that be some kind of like summation notation?
Yeah, I would think so, Landon.
Okay.
That's an interesting thing to kind of try to figure out. So if you shot one, waited a second, shot another one, waited a second, shot another one, waited a second, like coming up with some kind of a formula that would kind of tell you how fast you'd be going. And that's kind of cool because then you'd have, up here we had an initial velocity that was nothing, but sort of from then on, you would have initial velocities and then they would just grow and grow and grow. And so, yeah, you're exactly right. Let's do this the old fashioned way since it's, fairly easy. I mean, we usually wimp out on this kind of thing. Let's just solve it the old fashioned way. It seems like we should be in blue. So I'm going to take my 2 equations here in blue. And since the second one is solved for V of B, the velocity of the bullet, I'm just going to plug that in place. So I end up with 0 on the left equals, and I kind of like your idea of multiplying both sides by 32.2 just to get rid of it. So then I got 179.8 times the velocity of the dude plus 0.2 times the velocity of the bullet. But the velocity of the bullet can now be replaced with velocity of the dude plus 2,800. So now I've got one equation, one unknown. So that's kind of interesting. Notice what happens when you kind of add these two together. You distribute 0.2. You end up with your back to your full weight again, like 180 times the velocity of the dude plus 0.2 times 2,800. So you can see a shortcut could be made for this again. What we're trying to do is learn how to think so we can just solve problems. But if you're a skateboard, you're shooting yourself to work each day on your skateboard, and this is like the only reason you're doing physics, you can see there might be a shortcut here. Notice that this looks like, hey, combined weight. If I take the combined weight and take the bullet times the bullet speed, like a bunch of the work we did suddenly looks super easy, right? So in terms of an algebraic shortcut, sure. But we're just trying to understand these formulas and trying to learn how to think algebraically. So
yeah, my first thought would be, instead of messing around with multiple equations, the fastest way to do it would be to set the frame of reference, just to change the frame of reference to avoid that issue entirely.
Yep. Which is
because all we really need to know how to find is the change in velocity, right?
Yeah, that's right.
Is that a first velocity of the dude should be negative or no?
It's going to come out negative. Notice as I solve this, I took 0.2 times 2,800 and I got 560. If I subtract it to the other side, it becomes negative. So that's good, right? Because the dude's moving left. So notice I didn't have to put the negative in myself. It's happening automatically.
Okay.
So if I take 560 divided by 180, I get 3.11. So the velocity of the dude is negative 3.1 feet per second. That was our units, right? Feet, seconds, pounds. We didn't have to mess with any of that. Feet per second. So that's how fast the guy goes after one shot. And again, remember, because of friction, that's going to begin slowing down. But if there wasn't friction, and there wouldn't be much if you had a good skateboard and stuff, like you just roll at 3 feet per second for, some period of time. So I said, determine the speed of the man and the gun. So of course we got to go throw that back into this equation back up here. So if I subtract that from 2800, I get the velocity of the gun, or the bullet, is actually that much short of 2800, which is 2796. 0.9 feet per second. And again, it's really with respect to not the guy, but an observer. Does that make sense? Because the guy's in motion. With respect to the guy, the bullet's going 2800. So of course, this is kind of a fun example, just because, again, the problems in the book are just so sterile that, like, a cannon rolls down the hill and fires itself. You just feel like, when's this ever going to happen? But this is interesting to me. We gotta quit here, but this is interesting to me as a kayaker, because I'm in my kayak all the time and I'm doing stuff. And the kayak doesn't weigh very much. It weighs 40 pounds. And so when I tilt my body one way or another, the boat reacts accordingly. And so, learning how to roll in a kayak is really interesting, because what people do when they're upside down is they try to get their head out of the water to breathe, because that feels important to you. And interestingly, when you do that, because you're flipping your head up, your boat reacts by flipping you over. And so it actually kind of kills the roll. So the idea that, this guy does something, he moves his body, or, it doesn't have to just be a bullet, but just the concept that you move your arms out like this, that's going to cause a reaction. This is kind of the equal and opposite reaction concept. For every action, there's an equal opposite reaction. Which is, again, another one of Newton's laws at the start of this book in chapter 1. But I just find this, so practical, so realistic. If I'm in my car, or I'm on my bike, and I throw a newspaper at somebody's porch, the very fact that I threw that newspaper to the left is going to cause my bike to kind of go to the right a little bit, and I'll have to balance that. I have to make sure that doesn't knock me over, so to speak. And so, again, I'm interested in this making logical sense to you, more than just be able to answer kind of the boring book questions. So I got to give you a very important warning, though, about, I played around with this before class just so that I understood it, because you might want me to do this when I see you on Tuesday next week. But there's only 2 questions, 43 and 55, that you sort of should be able to do now, but 43 is really tricky, and I just want to give you a warning about it, because it's a neat problem. When I say tricky, I mean that's not the kind of question I would put on a test, but it is a good place for an assignment question. And the problem is, it looks so simple, because it's just a block sitting there on the ground, and it is a bullet getting shot into the block, and it asks how far will the block slide along the ground before it stops. It just seems like such a simple question, but it's really not. It's going to really make you scratch your head. Fortunately, you have the right answer, so you'll know when you get it right, if you do. But here's the hint that you've got to get. It just takes the same equation that we've been working on today, and this whole chapter, kind of the impulse momentum equations, but you're going to have to integrate a velocity equation, because it asks about distance. And in order to get a distance equation, you've got to integrate a velocity equation. So you're going to have a specific velocity equation that you create in this question. And if you integrate it, then you'll have an equation that will tell you what the distance is. And so it's really a neat question. It's why I signed it, but it's kind of dangerous. I definitely want you to understand this deeply before we're all finished. And if you need to ask me questions about it and so forth, great, we'll talk about it. But there's a hint. I can't see another way to do this. Like Landon was pointing out, sometimes there's, other ways to do things and so forth, but I can't see another way to do this question.
And this is 55, you said?
43.
Three?
It's the first question. It's kind of a ballistic pendulum problem, except it
Mm.
slides along the ground with friction. So think about that, like the ballistic pendulum, it lifted it up in the air, but since there would be friction of a block sliding on the ground, if you shot the block, does it make sense it would slide to a stop as soon as the force of friction and the time it took while it was moving along came to an end? It's going to come, all its energy is dissipated by friction. It's such a wonderful question, but it's just challenging. So make sure you make a note about taking the integral, and we'll look at it more later. I want you to thoroughly understand that question before we leave, just because it's so simple looking, but it's just not. It's a head scratcher. Anywho.
Go ahead.
Yeah, we got 15.2 chapter 3 questions, 15.3 2 questions. What about 15.4?
That is, and it shows this on the syllabus, but that just continues next week. Next week, we're doing 15.4 through 15.8. So we're going to be looking at impacts, and this is where, one thing hits something else and they bounce off, and they won't have to stay in a straight line. That's the thing that's going to be really cool. It's going to be, one ball hits another ball and they bounce off in different directions. And then we're also going to include that, I forgot what the word was, the elasticity, the coefficient of restitution, that how elastic the collision is, if you will. We're going to include that to sort of determine, where the balls are actually going to bounce and so forth. So we still have a lot to do in chapter 15, a whole week of it. So yeah, just 15.2 and 15.3. You only have 5 questions that you really should be giving me before the weekend is over.
So before we go, I actually did the math on it.
Mhm.
So for the original log problem, it actually makes a lot of sense